Welcome to ninth in the series of videos on simple machines, ninth video. And in this we will talk about single movable pulley. In the previous video we talked about a single fixed pulley, wherein the pulley was fixed on the top of a roof, and you have the load and you have the effort on this side. Ideal case, your effort is equal to load. Your velocity ratio is always equal to 1, and your ideal mechanical advantage is equal to 1 as well. Non-ideal mechanical advantage would be is equal to efficiency time VR. So it could be a little bit greater than or less than your actual velocity ratio. Now, a single movable pulley is where your pulley is movable, as you can see here. So you fix your one end of the rope and then you pull from the other end. A good example is you would be using these in your fishing boats. So let's say you have a fishing boat and you have a pole or something, wherein you want to lift something from down, and so you would pass on a pulley system, and you would pull this up, and this pulling up can be done by motor or hand or whatever, and here would be your load, right? So this could be one use case of how you would use it, and there are certain advantages. And one of the advantages is that there is about 2 ropes here, which is which the tension of both these ropes are balancing the load. And another observation that you can see here is that as your load goes up, if your load has to go up by a distance of let's say x, the sections of these ropes also, both the section of the rope have to move by a distance of x, so which means that so you have 2 sections of rope that has to move up. So to pull this up, you will have to pull this up by a distance of 2x. So if you want load to be moved by the distance moved by load is x, because there are 2 ropes which has to be lifted by x, your effort is moving up by 2x. So in a single movable pulley, your velocity ratio is going to be dE by dL, and that is equal to 2x by x, and that is always equal to 2. And your ideal mechanical advantage will be equal to, of course, your velocity ratio, and that will be equal to 2. But a non-ideal mechanical advantage would be efficiency times your whatever your velocity ratio is. And if you look at it from your mechanical advantage point of view as well, you can see that there are 2 tensions, and 2T is balancing the load, and your effort is you put in is only 1T. That means that the effort that you're putting it is actually equal to the tension of the rope that's here. Right, so your MA, you can look at it as load by effort, and that's also equal to 2T divided by T, and that's equal to 2. So you can look at it from a load angle, but usually it's better to come from velocity ratio and then assign the value for your mechanical advantage. Well, if you want to change the direction of the effort that you are putting in, then you can add a single fixed pulley along with this combination. So this is again one movable. So this is movable, and this is your fixed pulley. So this is used for changing direction, and this movable pulley, the single movable pulley, gives a mechanical advantage of 2. Now usually your velocity ratio is equal to, you can say in general your velocity ratio equal to number of threads pulling up the load. So here if you have 2 threads pulling up the load, 1 and 2, so your velocity ratio will be equal to 2. So here is a summary. A single movable pulley offers a mechanical velocity ratio of, this is your effort and this is your load, your velocity ratio of 2, and a mechanical advantage of, ideal mechanical advantage of 2, and you could actually change the direction of your force effort that you put in by adding a fixed pulley to the single movable pulley, and you apply effort in this case in this way, and your tension is both in this direction. So this doesn't change your velocity ratio in any way or your ideal mechanical advantage in any way.